Hey guys, today we're talking about the kinetic molecular theory in gas laws. They kind of all tie in. When you hear the word kinetic, I want you to think moving because that's what kinetics is. Okay, molecular, so we're talking about molecules, and then theory because we can't see how molecules move, but we have a theory on how they move, and we'll go into that. All right, so the kinetic molecular theory, by definition, is, let me move my face. There we go. The kinetic molecular theory of matter offers a description of the microscopic properties of molecules and their interactions, leading to the observable properties like pressure, volume, and temperature. This theory helps explain why matter exists in different phases, like solid, liquid, or gas. Okay, so again, this is us talking about molecular things, so super tiny things, but we can see how they interact by looking at things like how much pressure is in this container, what size is this container, how hot is this container, okay? So by looking at those and seeing the trends, we can determine how these itty bitty molecules are moving. All right, so here's the states of matter. All right, so you have solids where there's very little energy needed. Like that's why it's cold, because cold things don't take a lot of energy. There's not a lot of movement. They're packed pretty tight. As we start warming up, okay, the molecules can move around some more, and that's when we get liquids. Okay, but they're still touching each other for the most part, because that's why liquids are still together in a group. They're just not solid like an ice cube. So we're going from ice cube to water. And then whenever it evaporates, okay, when it's really hot outside, all right, that's when we get the gaseous form of water. So now the water's no longer touching each other. It has a lot of energy. That's like you can see the shadows of where it's been moving and where it's going to. Okay, so lots of movement. So as we're looking at this, okay, cold, solid, hot, gas. All right. The hotter something is, the more energy it has. We'll get more into that as well. All right. So for the kinetic molecular theory, there's 5 main parts. All right. Number 1 is that gas is mostly empty space. Okay. Gas is mostly empty space. It's composed of small particles that are far apart. Okay, so like if we go back, okay, the small particles that are far apart, there's lots of space between it. So that's when they say gas is mostly empty space. Okay, these particles are in constant random motion. You can't predict where they're going to go. Um, they just go bounce around and do their thing. Okay, particles collide with each other and the walls of their containers. These collisions is what creates pressure. Okay, so think of like a water bottle, think of a balloon. Okay, the more collisions it has with the walls of the container, the more pressure is inside of it. So that's why if you take a water bottle and you squeeze it really small with the lid on, an empty water bottle, excuse me. Okay, so empty water bottle, squeeze it really small with the lid on. Eventually the lid's gonna pop off, and that's because you're making it, as you're making the volume smaller, you're increasing the pressure, and eventually you just can't hold it and the lid explodes. All right. Number 4 says collisions are elastic. This means that the energy is not lost when particles collide with each other or the wall. All right, so it's not like it hits the wall and it just stops and falls. No, it hits the wall, bounces off, and keeps going, and it doesn't lose any energy when that happens. Really cheesy, but if you watch The Office, there's the episode where they're watching the TV screen behind Michael, and the square is moving in the thing, and they're trying to watch it as it hits the corner. Every time the square hits the wall, it just kept going. It didn't change its speed, and then eventually it hits the corner, and they were all happy. But that's what elastic is talking about. It doesn't just hit the wall and stop. It hits the wall and keeps moving at the same velocity that it was traveling. Okay. Number 5, the average kinetic energy of a gas molecule is directly proportional to the temperature. Okay, the less kinetic energy means the less movement a particle has, and this is how temperature connects with the phases of matter. Okay, again, that goes back to this right here. Okay, lower temperature means less movement. Hotter temperature means more movement. So the colder something is, the more likely it is to be a solid. Hotter something is, the more likely it is to be a gas. Okay, that's what that last one's talking about. So how do we observe this? How did scientists say this is what little bitty, tiny, itty bitty things do? All right. They focused on things that they can see. Okay. You can see how much pressure something has. Again, the lid pops off of the water bottle. Okay. You can tell how hot something is with the temperature. Volume, you can tell, like with most balloons or the latex balloons, okay, they start off really small. As you put air into it, the balloons get bigger and bigger and bigger. That's the volume changing, okay? And then moles. We're talking about moles again, right? Moles is just talking about like the number of particles, all right? So like when you're blowing up a balloon, you're putting more air, you're putting more molecules into the balloon. That's what we mean by moles in this. Okay, so this is just kind of breaking them down a little bit more. Pressure is defined as the continuous physical force exerted on or against an object by something in contact with it. Any wall containing a gas is constantly being bombarded with molecules it's containing. The more collisions it has, the more pressure there is. Okay, so like here, there's okay, for A and B, it's the same amount of particles. A has a lot more space, which means the particles can move around more, which means that there's less collisions with the wall. So this has low pressure. With B, okay, they push the lid down, so there's a lot less space, the same amount of particles, but when they have a shorter distance to travel, that means they're going to collide with the walls more. So that gives it a high pressure. Okay. Another way to look at pressure is, okay, here we have A and B again, but this time the volume stays the same for both containers. But notice how A has very few molecules and B has a lot of molecules. So A is going to have a lower pressure than B because A has less particles than B. And remember, excuse me, when I'm saying particles, I'm meaning moles, okay? Moles is the amount of the substance. So A has less substance than B does. All right, next we have temperature, and we've kind of already touched on it a little bit. Temperature is directly proportional to the average kinetic energy of a gas. Kinetic energy is represented by the equation Ke equals 1/2 mv squared. This is something you'll learn more about in physics, okay? What you need to know from this, okay, Ke stands for kinetic energy, m stands for mass, v stands for velocity. So on to the next bullet, as the temperature of gas increases, the kinetic energy is also increased. This happens because the mass stays the same, the particle stays the same mass, that doesn't change, okay? But if we start moving faster and faster, then our velocity is increasing. And when we increase the velocity, we're increasing the kinetic energy, okay? And the more something moves, the more energy it has, so the higher the temperature is going to be, okay? Think, solids don't move a lot, cold temperature. Gases move a ton, and it's a hot temperature, okay? Let's see. So to kind of help you think about that too, on a really cold day like the winter storm that we had, okay, most of you guys wanted to stay inside. You didn't want to go outside because it's too cold. You didn't want to move around. But as it starts warming up, as we were getting into the spring, hopefully you're wanting to get outside more and move around and just able to do more things outside. Okay, molecules are the same way. They don't like to move around when it's cold. They love to move around when it's hot. Okay, the other thing we're going to talk about is volume. Volume is defined as the amount of space a substance occupies. The space the substance occupies is referred to as either a fixed container or a flexible container. Fixed means the size of the container stays the same. Okay, think glass jars or this water bottle. Okay, it's a hard surface, it doesn't change. Okay, so this is a fixed container. A flexible container means the size of the container can change. All right, so if I have like a Ozarka or Dasani water bottle, okay, how you can squish those to make them smaller, that's a flexible container. I can't squish this kind of a bottle. All right. So that's the difference. Fixed stays the same. Flexible, the size can change. All right. That's why I have the balloons, because balloons start off small but then get larger as you blow more air into them. Okay, that's a flexible container. Volume, the unit that we use with volume is liters. So anytime you see something with liters next to it, automatically assume that's your volume variable. All right, then we have moles. Okay, and we've already talked about moles a few times, so hopefully you're starting to see that moles represents the amount of particles or molecules, sorry, I almost combined those words, found in a container. Moles is identified by the letter N. So when we're getting to the equations later this week and you see the letter N, that stands for moles. They don't use the letter M for moles, which would make sense because it's already being used for mass in meters. So they use the letter N to keep from getting confused. All right. But again, moles is just talking about the number of particles of something. Okay, so this unit that we're doing is really going to be focusing on gas laws. Let's see, gas laws are a way that we can predict how the pressure, temperature, volume, and moles interact with each other using mathematical equations. So there are some conceptual parts to this unit and there's math parts to this unit. But the math parts that we're dealing with are more like algebra 1, solving for x kind of things. So don't be too worried about that. Okay. The first gas law that we're going to talk about can be the trickiest because it has a little bit of conversion factors to it, but the rest of them are pretty solid, and you'll see as we go throughout the week. Today we're focusing on Dalton's law of partial pressures. Okay, Dalton's law of partial pressure states that the total pressure of a mixture of gases is the sum of the partial pressures of its components. Okay, so here's my picture example for that. Okay, so here we have oxygen, nitrogen, a little tiny bit of argon, water vapor, and carbon dioxide. Okay, this all makes up the air that we breathe. So like when you're doing a scuba tank and you're about to go diving, what they're doing is they're taking different parts of the air, okay, and combining it into one container. But as you start adding like 1 mole of oxygen, 2 moles, or sorry, we'll say 2 moles of oxygen, a half a mole of nitrogen, a tiny bit of argon, the pressure starts adding up. That's what Dalton's law of partial pressure is, the total amount of gas in a closed container. Okay, so this is our equation for it. So in just a few seconds, I'm going to switch over to writing on paper, and we're going to learn how to solve these problems. So ready, set, go.
Okay guys, so I'm going to be moving to paper to show you these last few examples. All right, so with Dalton's law, when we're talking about units of pressure, okay, pressure often comes in varieties of units, or like just a variety of ways. So we're going to use the following to kind of help us with conversions. A lot of times we see pressure in science world measured in atmospheres. Okay, temperature, among other things, is taken as millimeters of mercury. All right, and I'm marking these as different colors because I'm going to be using these colors throughout the examples. And we also use the unit torr. And if you notice that millimeters of mercury and torr are equal to the same number. Okay, then we have kilopascals. Okay, that's what kPa stands for, kilopascals. And last, we have PSI, which is pounds per square inch. Okay, we hear this one a lot, like if you're filling up your tire, like how many pounds per square inch or how many PSIs is your tire, okay? Because again, tire is all about pressure and you want to have the right amount of pressure as you're driving your car, all right? So these are the units that we're going to be using. Now, as we're using this, okay, these are all, like this is the conversion factors that you need. Okay, so this is like saying that 1 atmosphere is equal to 101.3 kilopascals. All right, sorry, that's a typo. That should be a lowercase a. All right, or like saying that 14.7 psi is equal to 760 torr. Okay, so these, like, again, 1 atmosphere is equal to 101.3, 14.7 is equal to 760. All right, so these are all equal to each other. All right, now for Dalton's law, we said that the total pressure is equal to the parts of all of the pressure. So when we're doing this, we have to make sure that the pressure has to be in the same unit. Same unit for Dalton's law. Okay, so pressure has to be in the same unit for Dalton's law. So we've got to work on conversions. So let's say we have a problem that has 3.2 atmospheres and it needs the total pressure to be in kilopascals. All right, so what we're going to do is we're going to start with the 3.2 atmospheres that it gave us. And to do a conversion factor, sorry, I thought I had my papers lined up right. All right, so now we're going to do a conversion factor, which is also known as dimensional analysis, also known as railroad tracks. Okay, so you're always going to start with what you're given, and it's just going to be one step, so you can draw the tracks just like this. To figure out what numbers we're going to use where, that's when we're going to come back and we're going to look here. Okay, so all right, so if we have atmospheres here, then that means we have to have atmospheres right here. What number goes with atmospheres? 1. Okay, what unit is it asking us to convert it to? Kilopascals. And what number goes with kilopascals? 101.3. Okay, so this is what the dimensional analysis looks like. Again, for this second step, I use the numbers from up here to go with the units that we have. All right, so since this number is on top, I'm going to do 3.2 times 101.3, and then we'll divide it by 1. And when we do that, we get 324.16. All right, and in this case, for my answer, I'm just going to round it to three digits. So I'm going to make it 324 kilopascals. Okay, so let's try it for the second one. Okay, if we have 1,021 millimeters of mercury, So we start with the number that we're given, draw one train track. Okay. What number goes to millimeters of mercury up here? 760. Okay, so we're going to write 760 millimeters of mercury down here. And then it's asking us for PSI. So go ahead and look. What number goes with PSI? Hopefully you said 14.7. All right, so just like we've been doing with stoichiometry and moles, you're going to multiply on top. So 1021 times 14.7. And then you're going to divide it by 760. And that should get you in the calculator 19.748. And again, I like rounding things to at least 3 digits. So for my final answer, I would say 19.7. Okay, you don't have to do conversions every time, but if the pressure's not in the same unit, then you've got to change it to the same unit. This is how we do that. Okay, so let's look at some example problems. All right, so I'm just going to kind of keep this at the top here. Example 1 says calculate the total pressure if 2 atmospheres of gas A and 7 atmospheres of gas B are mixed in a closed container. Okay, so this is atmospheres. My gases are in the same unit and it's not asking for my answer to be in a specific unit, so I'm going to keep these as atmospheres. Okay, now remember, for Dalton's law of partial pressure, it's P total is equal to the parts. So here we have part A, and then we have part B. Okay, so for this one, we're going to do 2 atmospheres plus 7 atmospheres. All right, and what's 2 plus 7? All right, hopefully you said 9. Okay, so this answer is 9. This is the total pressure of the container. Okay, sometimes they are this easy. Sometimes they get a little bit more complicated. So let's look at number 2. Okay, it says some noble gases are stored in a container. If the individual pressures are that neon is 450 millimeters of mercury of pressure, helium is 1.26 psi, and krypton is 70.2 kilopascals, it wants to know what the total pressure is in atmospheres. Okay, so this specifically tells us it wants our answer in atmospheres. But right now, when I look at it, I have millimeters of mercury. I have PSI. And I have kilopascals. Okay, so I've got to convert these 3 numbers to make them all equal to atmospheres. Okay, so I'm going to start and do those 1-step conversions like we did earlier. If you think you can handle those, try it on your own. If not, let me do one with you and then you try it. Okay, so here we have 450 millimeters of mercury. And we're trying to figure out how many atmospheres it is. Okay, and we have 1.26 psi. We're going to try to figure out how many atmospheres that is. All right, and then finally we have 70.2 kilopascals. And again, we're trying to solve this to atmospheres. Okay, so we'll do this one at a time now. Again, if at any point you're feeling comfortable with this, stop, try to finish it on your own, and then check your answer with mine. Okay, so we have millimeters of mercury here. That means millimeters of mercury goes on bottom of this step. When I look at the top, the number 760 goes with it. So 760 millimeters of mercury. And we're trying to solve it to atoms. So when I look up here, the number that goes with atoms is 1. So this is 1. And I said atoms, I'm sorry, I mean atmospheres. All right, so now I can do 450 times 1 divided by 760 and look at my answer. Okay, let's go ahead and finish these two. All right, so what number goes with PSI up at the top? 14.7. And then what number goes with atmospheres? 1, because we just did that. All right, for this last one, if we're still looking for atmospheres, that means we're going to have 1 atmosphere up top. All right, and what number goes with kilopascals? 101.3. Okay, so now go ahead and put these all in the calculator. All right, 1.26 times 1 divided by 14.7, 70.2 times 1 divided by 101.3. All right, when you do that, okay, we should get paper. There it is. Okay, so let's see, this is for P and E, this is for PHE, and this is for PKR. Okay, so P and E ends up equaling 0.592 atmospheres. All right, PHE, sorry about that, PHE is equal to 0.086 atmospheres. And this last one, P krypton, is equal to 0.693. Okay, remember that it's the total is equal to the sum of all the parts, so it's going to be adding all of these together. Okay, so when we add all these together, we end up getting 1.371, or you could say 1.37 atmospheres. Excuse me. Okay, so that's Dalton's law of partial pressure. It's adding things together, okay, to figure out the total. The most confusing part about it is making sure you get everything in the same unit, because you can't add apples and oranges. You have to get them all to be apples or all to be oranges. Okay, that's what this is talking about. That's why we converted all these to atmospheres and then added it up. Now, know that you can also see questions asked where it gives you the total, and maybe it gives you 2 of the parts, and then you have to solve for the third part. So how do you think you would do that? Okay, you would do that by starting with your total, subtracting the 2 parts that you do know, and what you have left over is your unknown. Okay, so just be ready to see examples like that as well. All right, so go ahead and start working on the knowledge check for today, and then you're good to go.